The topic of this lecture is metric learning, and it's going to be building on some of the ideas that we presented earlier about linear dimensionality reduction. We're also going to be looking mostly at linear approaches here, but we're going to start taking into account class structure as well, so the actual class of different data points. And this leads us into a new corner of the field known as metric learning. All right, the main objectives of this presentation will be to help you understand the Mahalanobis distance, which is probably the most important class of distance metrics. And then we'll know how to apply metric learning to a classification problem to get improved performance. All right, so here's just a real simple example to motivate why we might be interested in learning distance metrics. And it involves predicting heart attacks. So here we've got a table of attributes for different individuals with different numerical attributes. So we've encoded gender as either 0 or 1. We've included the age as well, the individual's weight, which might be relevant to whether they're going to have a heart attack or not. And we've also included their income, right, which might or might not be relevant. One thing to note about this particular formulation is that all of these different attributes have wildly different scales, right? So income could differ widely by thousands, whereas weight is probably going to differ by tens at most, and age maybe by just 10 or so years. Gender is never going to differ by very much at all. So these attributes are they all have different scalings in this input space, but there's nothing in the data that would indicate that, right? So if we just throw our standard pattern recognition algorithms at this, or our standard dimensionality reduction algorithms, they might be unduly influenced by a feature like income, right, which is going to have very high variance relative to the others. So, and another related problem is that there may be correlations. You can imagine as we add more features on there could be spurious correlations in the data set that make different attributes totally redundant with each other as well. So particularly for nearest neighbor methods and methods like that rely on calculating distances within the attribute space, those are definitely going to be biased by the income attribute as opposed to some of the others that might actually be more relevant to the heart attack problem. So how do we solve this? Well, a traditional solution to resolving this might be to apply some sort of pre-processing strategy. We can do normalization, maybe standardize things so they have mean 0 and standard deviation 1. That's a fairly common approach. And there are all sorts of pre-processing methods that we can apply. But the intuition behind metric learning is that maybe if we incorporate some class information from our training set, we can do even better. And we can define distances in this space that are actually more relevant to the task at hand than we would if we simply relied on intrinsic properties of the data itself. All right, so to summarize, measuring distance is a really critical part of pattern recognition, and this is not just for local methods too. This is for all sorts of parametric methods for classification and regression. Until now, we've sort of been letting the data itself define our distances, but there are challenges with this that we noted before. And additionally, recall that Euclidean distances are less meaningful in high dimensions anyway. So even if our data is perfectly isotropic and uncorrelated with each other, and all distances mean the same thing and along all attributes, those Euclidean distances are going to be less valuable to us as we start moving to high dimensions just because of the curious geometry of these high dimensional spaces. So how can we resolve this problem? Well, metric learning is based on the idea that we can define new distance metrics, new rulers for measuring distance in higher dimensional spaces that are based on properties of the data itself. These are non-isotropic distances that reflect some intrinsic structure in the data, right? So this is a really elegant depiction of what we're talking about that involves moving from Euclidean isotropic distances to a Mahalanobis distance metric. So on the left side, you see a data set of, I guess, 6 points. Here, the data point's color represents their class. So you can see that the yellow points are all of one class, and they're sort of distributed more or less along a line. And there are also a couple of points having different class values to the north and south of them. Note that if we're trying to classify the query point in the center and we want to enclose the entire training data set of yellow points, we have to look out far enough that we're actually the end ball is encompassing all of our data, including the blue and the red. So really what this suggests is that the Euclidean data, the Euclidean distance metric, which is the same in all directions, really doesn't reflect the class structure in the data that tends to be distributed along this line. So Mahalanobis distance metric is more akin to, say, an ellipsoid. And that's what's portrayed in the panel at right. Here we're looking at a Mahalanobis distance, and here the n ball in this Mahalanobis distance measure encloses all of the yellow points while avoiding the data points of different classes. So that our ruler in this space actually reflects the structure of the data. So how do you calculate a Mahalanobis distance? Well, we know how to calculate a Euclidean distance, right? It's just the square, basically the squared sum of differences, take the sum of squared distances and then take the square root. The Mahalanobis distance metric is almost the same, except in there's an inverse positive semi-definite matrix that I've indicated here with this sigma. So, and you may note an analogy with the covariance matrix from data sets that we've seen before, say in the PCA lecture that preceded this one. And that's not an accident, because actually you can easily use a covariance matrix here to whiten your data. Just take its inverse and scale all of the dimensions and correlations appropriately to basically undo the covariance properties of the original data set. And this whitens the data. It makes everything isotropic so that the distance we calculate will be now adequate it will reflect the correlations in the sigma matrix. One can easily show that this expression is actually equivalent to a linear pre-transformation of the data. So here we define this matrix sigma as V transpose V, and push it through some algebra and reveal on the bottom line there of the expression that it's actually equivalent to pre-multiplying all of our data by a new basis V. So really what this means is that in order to calculate a Mahalanobis distance, we can just take some linear transformation of the data and then apply our Euclidean distance in that space, and it's the same as the Mahalanobis distance metric. And note that you can calculate this decomposition for any positive semi-definite matrix. It's possible to decompose it into the V's as we've done here. So there's a natural relationship between the Mahalanobis distance metric, or this ellipsoidal distance, and the linear dimensionality reduction strategies that we've explored in previous lectures. All right, this leads me to the wild and woolly topic of metric learning, which is an area of a lot of active research. Most modern metric learning research, that is work to learn these distance measures, treat it as a convex optimization problem. So they take a Mahalanobis distance and then have some constraints on that based on the class structure in the data, such as data points having similar class must be close together, data points having different class must be far apart, right? And then treat it as an optimization problem and apply techniques from operational research and other disciplines in order to tune that Mahalanobis distance metric, that sigma matrix, to best separate the different classes, right? And there are challenges there, of course, in keeping the matrix positive semi-definite, which it must be in order to be a valid Mahalanobis metric, but that's the part of the research that's going on. And there are lots of applications for this, which include computer vision, information retrieval, where you could be looking in databases, right, to find something that's similar to your query, which could be expressed as an image or a document with a bunch of text, right, which would have potentially thousands of different word attributes, or in biometrics, where you're looking at gene expression information, right? You could easily get data points of thousands or tens of thousands of attributes there. So it becomes important, if you're doing similarity queries in those sorts of settings, that you have an effective distance metric on which to do that query. So so this is the modern topic of metric learning. And here are a couple examples of the different methods that have been proposed in the literature for learning these distance metrics. Most of this list are Mahalanobis distance metrics, or linear pre-transformations of the data. This list is from Ballet, Hubbard, and Seban et al. And it simply gives you some intuition for the breadth of different algorithms that are available to do metric learning. Now we're going to put most of this aside for now and instead talk about an oldie but a goodie. That is a classical approach for metric learning that works in many cases and has the additional property that is pretty robust and reliable and pretty easy and cheap to implement. That is pretty simple to implement. I think I mentioned this already once before, the relationship with linear dimensionality reduction. That is, if this linear pre-transformation represents a subspace of the data, that is, the covariance matrix isn't full rank, or V has fewer columns than the full space of the data, then this actually equates to a dimensionality reduction. And in that case, it's akin to PCA or some of the other methods that we've shown previously, the only difference being that here the dimensionality reduction is taking the class structure into account and trying to separate the different classes from each other. Okay, so here's our classical approach to metric learning. And this is a method that dates back to Fisher, I believe. It's multiclass discriminant analysis. It's a generalization of Fisher's linear discriminant to the case where we have several different, many different classes, up to k different classes in this case. So we start with our data set of data points that's labeled with up to k different values. The idea is to learn a Mahalanobis distance metric that best separates these classes from each other, where we'll define separation shortly. The output of this procedure is a linear projection of the dimensionality up to k minus 1, right? So it will also reduce the dimensionality of our input space. And like I said, if we just use a 1D case with two classes, that's equivalent to Fisher's linear discriminant analysis. All right, so here are some definitions to get us started. First, I'm going to define the class mean as the mean of all the data points having a certain class label ascribed to them. So we have a class mean for each one of our k different classes. We're also going to define scatter matrices to represent the spread of the data. Here we define the within-class scatter matrix in fashion similar to the sample covariance matrix. So we're just looking at squared distances against the mean. And we do that for each class independently. If you take the sum of all the within-class scatter matrices, then you get the total within-class scatter matrix for that data set. And here I've just represented this graphically on the right side as ellipsoids. So each ellipse here has its own, it represents data from a different class in our data set. And the within-class scatter is represented by the blue lines, right? So that basically that measures how compact all of these different class distributions are, right? We're also going to define a matrix known as the between-class scatter matrix, which measures how well these different ellipses are separated from each other. So we take the mean of the entire data set, that is mu, and look at the difference between that and the mean of all of the classes independently. So this is represented in the image by the green arrows that show the separation of the different ellipsoids. So we have two measures of scatter here, the within-class scatter and the between-class scatter. So if we want to improve the separation of the classes in our projected space, the idea is to come up with a projection that shrinks the within-class scatter. That is, we want all of the class distributions to be as compact as possible in the projected representation. At the same time, we want to increase the between-class scatter. We want the classes to be well separated from each other. Right? And so how do you define this? Well, we measure the determinant of the scatter matrices, which you can think of as a sort of a measure of volume in high dimensions for these positive semi-definite matrices. So here's our objective. We find the projection V to maximize the ratio of these determinants. That is, the ratio of the between-class scatter over the within-class scatter. We're trying to increase the numerator and decrease the denominator. This is known as the Rayleigh coefficient, and there exist lots of straightforward ways to calculate this, but probably the most common one is to simply solve this generalized eigenvalue problem, where you have the within and between-class scatter matrices on either sides of this expression, and then the vector of eigenvectors, which is, the matrix of eigenvectors, which is V, and then eigenvalues represented here by lambda. So solving this generalized eigenvalue problem with standard numerical software will give you the projection that best separates the classes according to that criterion that we established in the last slide. All right, so I want to close with a quick example of how this can actually be used in practice. So here we're going to look at an application in automated image analysis. So we're looking at analysis of geologic images in particular. This is work by Francis et al. In ICIRIS of 2014. The idea is to perform segmentation of images. You may be familiar with image segmentation problems, and here we're looking at basically clustering data points, but we want to cluster data points in a way that's relevant to the task at hand, that is relevant to the geologic content of the images. So we're going to assume that our data cloud is made up of points which are vectors of pixel attributes, which might include color attributes as well as texture attributes. And the objective here is to learn a projection that improves the quality of our image segmentation. That is, we want some distance where, we want some distance metric where distance in the projected space represents a sort of geologic distance in the image space. So here's an example of what the automated clustering should look like. So here's an example of a k-means clustering with just 2 clusters. You can see we have a rock outcrop on the left, and we've applied unsupervised clustering to that, and it nicely splits the image into 2 different classes at right, and this corresponds quite well with the geologist's interpretation of the scene. And so we'd like to do this for all sorts of outcrop images, but it doesn't always work. You can see that often the pixel values themselves don't actually reflect the geologic content. So this is quite obvious in this image where we have fractures that are a lot darker than everything else, but they aren't. So these fractures aren't necessarily geologically interesting. They don't correspond with the composition of the rock that we're trying to recover, but k-means clustering is biased by the values of those pixels, that is the extreme attributes, the extreme dark intensity of those pixels, right, which cause it to be very distant from everything else, so the fractures appear as their own cluster, right? We'd like to avoid that. We want some different distance metric that will allow the k-means segmentation to overlook some of these incidental features like fractures and instead focus on the features that are most relevant, that is the color and texture cues that will tell us where composition is actually changing. So Francis et al. Applied the multiclass discriminant analysis to this problem. And here you see a projection of data points from rock outcrops. This rock outcrop had 3 different classes, and you can see that the MDA projection, that is the multiclass discriminant analysis, does a much better job of separating these classes than traditional PCA or indeed clustering on the raw feature space would. So by training on labeled examples from one image and then applying that distance metric to another image, we can actually teach the system how to perform clustering better in order to recover geologic classes as part of the cluster. So here's a visual example on that image that I showed you before. The fractures, instead of getting their own cluster, after we learn the distance metric appropriately, we can get the system to actually autonomously recover the compositional differences in the rock and avoid the fracture confusion. So this is just one of many examples where multi-class discriminant analysis can improve unsupervised clustering. So this pre-transformation that we've trained on labeled data can be used to improve a totally unsupervised clustering approach on future images. Okay, so a quick summary of what we've covered in this lecture. We talked about Mahalanobis distance metrics, which are sort of an ellipsoidal generalization of the Euclidean distance. Applying them or measuring Mahalanobis distance is equivalent to applying a linear transformation on the original data set. Metric learning can outperform purely unsupervised dimensionality reduction by accounting for the structure of classes. And we've additionally shown how multi-class discriminant analysis is a particularly useful form of metric learning that can provide projections of dimensionality up to k-1, where k is the number of classes in your data set.